Today, we're going to dive into the architectural style that powers so many of the modern, massive-scale apps we use every day. We're talking about event-driven systems on AWS. It's all about building systems that don't just wait for commands, they react to what's happening in real time.
So, let me ask you this. Have you ever been there? You push what feels like a tiny, harmless code change, and then, boom, the whole system just grinds to a halt. It is one of the worst feelings for a developer, and you know what? It almost always points to a much bigger problem with the architecture itself.
And that problem often has a name: the monolith. This is an architecture where your entire application, the UI, the business logic, the database layer, everything is all one single, giant, tangled-up unit.
Now, with a monolith, everything is just jammed into one big box. All the components are so tightly woven together that if one little part fails, it can create a domino effect and take the whole system down. And scaling? It's a nightmare. You have to scale the entire application, even if only one tiny feature is getting hammered with traffic. Microservices, on the other hand, just smash that box into little pieces. You get these small, independent services that are loosely coupled, which means you can develop, deploy, and scale each one on its own. But, okay, breaking up the monolith creates a brand new problem. How do all these little independent services actually talk to each other? That right there is where the event-driven solution comes in. We shift from services directly telling each other what to do to services simply reacting to events that happen around them. So what even is event-driven architecture, or EDA? Well, it's a design where your services communicate by basically shouting out things that have happened. We call these events. This completely decouples them. The payment service doesn't need to know the shipping service even exists, it just cares about payment-related events. This makes your whole system way more resilient, way more flexible, and so much easier to scale.
On AWS, building an EDA means you've got this amazing toolkit of messaging services at your fingertips. So let's look at the three big ones you'll be using pretty much all the time.
First up, we've got SQS. The easiest way to think about it? It's like a digital post office box. One service, the producer, drops a message into a queue, and another service, the consumer, comes and picks it up whenever it's ready. It is absolutely perfect for that one-to-one asynchronous communication, making sure a message can just wait patiently until it's time to be processed.
Next up is SNS. Now, if SQS is like a private letter in a post office box, SNS is a giant broadcast megaphone. A producer sends just one message to an SNS topic, and that message instantly gets blasted out to all the different services that are listening. We call this a fan-out pattern, and it's fantastic for one-to-many notifications.
And finally, we've got EventBridge. You can think of this as the smart central switchboard for your entire architecture. It is so powerful. It can listen for events from hundreds of sources, not just other AWS services, but your own apps and even third-party SaaS tools. And then it uses these really smart rules to route those events to exactly the right place.
Okay, so this table really just nails the decision-making process. If your goal is just simple, super reliable decoupling between two services, point-to-point, SQS is your go-to. If you need to blast a single message out to a whole bunch of subscribers at once, that fan-out pattern, you're going to want SNS. But when you need to run a whole orchestra of complex events from lots of different sources with all kinds of fancy filtering and routing, that is the job for the central event bus, EventBridge.
All right, theory's one thing, but let's actually see how all this stuff comes together in the real world. We're going to sketch out a blueprint for a classic e-commerce application.
Okay, so it all kicks off when a customer clicks Buy. Our application doesn't directly call another service. Nope. Instead, it just publishes an order-created event to our central EventBridge event bus. It just puts the news out there for anyone who cares to listen.
Now EventBridge, our smart switchboard, sees that event and immediately jumps into action. Based on the rules we set up, it sends the information in two directions. First, the inventory service, which is listening for exactly this kind of event, starts checking the stock levels. At the exact same time, EventBridge puts a separate process payment message onto an SQS queue. And this is so important. It decouples the payment. So even if the payment provider is being slow, it doesn't hold up the rest of the entire order process.
So once the payment service successfully processes the charge, it publishes its own event, Payment Processed. This new event hits an SNS topic, our megaphone, which then instantly fans out the notification. The shipping service gets the signal to start packing the box, and an email service gets the signal to send that confirmation email to the customer. See? It's all happening in parallel, and everything is beautifully decoupled.
So our happy path looks pretty great, right? But distributed systems live in the real world, a world where networks get flaky and services go down. So let's talk about how we handle the chaos.
One of the most common headaches is the duplicate message. See, to be reliable, these AWS services guarantee what's called at least once delivery. That means a little network hiccup could cause a message to be delivered twice. And in our e-commerce app, that can mean, well, it can mean charging a customer twice for the same thing. Yikes!
The solution to this is a really critical concept called idempotency. It's a fancy word, but it just means designing your service so that receiving the same message 10 times has the exact same result as receiving it just once. So our payment service, for example, would be smart enough to check the order ID, see that it has already processed that payment, and then just quietly ignore any duplicates that come in.
But what about messages that just keep failing for some other reason, like a bug in the code or bad data? We don't want them to just get stuck in the queue forever, blocking everything else behind them. And that's exactly what a dead letter queue or a DLQ is for. It's a safety net. After a message fails a few times, it gets moved to the DLQ, so you can go figure out what went wrong later without losing any data.
Now, all these design choices really highlight a fundamental law of distributed systems called the CAP theorem. Event-driven systems make a very specific trade-off. They prioritize being available and tolerant to network partitions, which basically means the system is designed to stay online and keep working even if some of its internal parts can't talk to each other. The trade-off? They accept something called eventual consistency. This just means it might take a moment or two for data updates to be perfectly synced everywhere. For our shop, that's a fantastic deal. A customer might have to wait an extra second for their confirmation email, but the website itself never goes down.
Okay, so let's zoom out. What's the big picture here? What are the main takeaways? Why is this architectural style such a game changer for building modern apps?
You'll want to choose an event-driven architecture when you know you need massive scale, when your different teams need to be able to work on their services independently, or when your business logic is just naturally asynchronous, like our whole order processing flow. It is a strategic choice for building systems that are flexible and built to last. And if you decide to build this way, please remember these best practices. They are not optional. Always use dead letter queues. You have to have a plan for failed messages. Always build your services to be idempotent so you can handle duplicates safely. You absolutely must have great monitoring and tracing because you can't fix what you can't see. And finally, lock everything down with the principle of least privilege. Make sure your services only have permission to do exactly what they're supposed to do and nothing more. So this really brings us to a final question I want you to think about for your own work. Is your system designed like a rigid, fragile monolith built to break under pressure? Or is it a dynamic, flexible network of services, built to react and adapt to whatever the world throws at it? The choice? Well, it can make all the difference. Thanks for joining this explainer.